Okay, so welcome to the part 5 of our lecture on shear and moment diagrams. Okay, so we have here another example. So this will be our third example. Okay, so our first example was discussed on um, part 2 and part 3 respectively, in which part 2 and part 3 are solved um, in different manners. One by the third one, or the last, the part 3 is actually through shear and moment equations. Okay, so today we're gonna solve another problem, this one. Okay, so please consider uh, this this beam. Okay, so obviously this beam is a simple span beam in which is pinned at left support and ruler at right supports. Okay, so first, okay, we will write its respective um, reactions. Okay, so since this is pinned, it has two reactions. It has both vertical and horizontal reactions. And for B, we have uh, only vertical reaction. Okay, so since ruler, it is a horizontal ruler, so therefore it can move from left to right. So because of that, it cannot resist horizontal loading. So it has only one reaction, which is vertical. Okay. So speaking of, before we can compute the shear and moment, we can construct the shear and moment diagram. First step we should do is to compute first the reactions. Okay. So here, um, okay, so first, we sum up moments and forces and moments and equate them to 0. So first, we sum up moments horizontal, or x is equal to 0 to the right as positive. Okay? So in the figure, we have only one horizontal force, and that is Ax. And so Ax is equal to 0. Okay? So I will, okay? So I will make it clear. Ax, Ay, okay. And then, next, we sum up moments at y-axis equal to 0. So, let us say upward as positive. Okay? It's just an initial assumption. So, ay plus by minus 75 minus, okay? So, one thing we should do in this problem, okay, is to compute the area of this triangle. Okay? So, before we compute the area of a triangle is equal to 1/2 BH, right? So let us say that your B is 4.5, okay, 4.5, and your H is 16. So just like that, 1/2 times 4.5 times 16. Okay? Just like computing your area. So we have AY plus BY minus 75, 1/2 times 4.5 times 16 is, okay, let's use calculator so that it will not be wrong. Okay, 36. So therefore, your AY plus BY, transpose it, okay, 75 plus 36 equals 111. Okay, so take it as it is, and then we have another formula. Summation of moments is equal to 0. Okay, so let us consider a point where we will sum moments with. Okay, let us say B. Okay, so if that is the case, we take B as a fulcrum point or a steady point, and everything in this drawing rotates. Okay, so since AX has no, okay, is already horizontal and relative to this line, this, so it has zero. It has zero effect on your beam. So only these vertical ones. Okay. So we have, since B is your fulcrum or steady point, everything rotates. So this AY, okay, so let us assume a direction for your movement. So let us say counterclockwise as positive. So if BY is your fulcrum, your AY will rotate relative to your B is counterclockwise. So your AY is positive. So AY times, okay, relative to B. So AY times the moment arm. Okay? So since AY is vertical upward, its horizontal or its perpendicular distance is the horizontal distance. And this horizontal distance is should be relative to B. So the distance relative to B, okay, the horizontal distance of this AY relative to B is 2 plus 2 plus 4.5. So 2 plus 2 plus 4.5 is 8.5. Okay? So that is the moment arm. The moment arm, remember class from your statics, is always perpendicular to the direction of your force. Okay? And then we have another force, 75. Okay? Relative to B, this is your fulcrum. So your 75 will rotate. Okay? Imagine it will rotate. It will rotate. Okay? Okay, we have assumed clockwise. Okay, not counterclockwise as positive, but clockwise. So this is clockwise. AY is positive. This 75 is counterclockwise. So we have negative 75 times 2 plus 4.5 is, okay, 6.5. And then we have, okay, since clockwise is positive, so this is fulcrum. So this point will tend to rotate counterclockwise. So since our clockwise is positive, so this is negative. So negative, the area, okay, 1/2 of the area, 4.5 times 16 times the moment arm. Okay, remember always that the centroid of your triangle is L/3 from here. Okay, so since this is your L/3, L is 4.5. So your L/3 is 4.5 divided 3 is 1.5 meters. So in other words, this is 3 meters and this is 1.5 meters. Okay, so relative to B, the direction of your BY relative to B is 1.5. Okay, 1.5. So we have multiply it by 1.5 is equal to 0. Okay, so that is how it is. Okay, so we can now compute your AY. So AY is, okay, 7.5 times 6.5 plus 0.5 times 4.5 times 16 times 1.5 divided by 8.5. So we have, okay, so let's check 4.5 times 16 times 1.5 relative to B. Okay, so we have 63.706 kilonewton. So since this is positive, so our assumption that the direction of AY is positive is plus 1. Okay, 63.706. And then we can substitute it here, this equation. So AY plus BY equals 111. And we know that AY is 63 0.706 plus By is equal to 111. So therefore, we can compute the value of By. Okay? So 111 minus answer is 47.294 kilonewton. Okay? So since this is positive, so our assumed direction is valid. Okay? So your Ay here is 63.706 kilonewton and your By is 47.294 kilonewton. And this is Ax is 0. Okay? So now, since we have the reactions, we can already construct our shear and moment diagrams. Okay, later on, I will erase this one. Yes, please take your time looking at this. And then, we will construct the shear and moment equation so that we can draw your shear and moment diagram. Okay, so let us say this is your Vx and Mx diagram or shear diagram and moment diagram, and this is the line that represents the zero value. Okay, so since we have transferred these values to this, okay, so in this area we will solve our shear and moment equations. Okay, we will construct our shear and moment equation. So may I erase this one since the values is already transferred here. Okay, so since this is a video, you can always repeat the portion of the video, of our video in which you have not understand very well. Okay, so please take note that this is the part 5 of our lecture. Okay, so if you have not seen the part 1 to 4, please do watch it first. Okay, so let us say shear and moment equations. Okay, so we write from A. Okay, so first we will divide this beam into sections. So we have 1, 2, 3 sections. Okay, so this first section is from this point A up to this point where 75 kilonewton starts, and then from where 75 kilonewton starts until where your triangular load starts is section 2, and for the whole duration of your triangular load or whole length of your triangular load is section 3. Okay, so we have AY here is 63.706, and then we have AX equals 0. Okay, so let this is within your section 1. So this value is maximum is 2, but at any value of X, your 75 may not come. Okay, so somewhere, let us say 1.5. So your X is at section 1. Okay, X equals to 0 to X is equal to 2, which means within from range 0 to 2. So 75 kilonewton is not included yet. Okay, 706. So here V is, since there is no other force here, it is 63.706. And your moment is, this is a point load, upward. So this is 63.706 X. Okay, for the second one, at section 2. So this is your shear and moment equation in section 1. And section 2, from x is equal to 2 to x is equal to 4. Okay? So from that value, okay, x equals to 2 and to x equals to 4, we have ay is equal to 63.706. Okay? So let us conserve our space. So let us put it here. 75, okay. 75 kilonewton. And then at any point here, okay. AY is 63.706. This is 2 meters and this whole duration is x. In which it is, this x is within 2 and 4. Okay, in bit any the minimum value is 2 and the maximum value is 4. Okay, we have ax equals 0. Okay, we don't need to rewrite this one, but somehow for emphasis I do that. Okay, so your v, we have here an upward value, so 63.706, and then we have a downward value here which is 75. So we have v is equal to negative 11.294. So this is the value of your v from 2 to 4. And then your moment, okay. So let us consider this one also. This is from our first example, for example 1. Okay, may I see it? You can see it clearly. Okay, since we have a point load P, okay, we have negative P. So this is what we do here, negative P. Okay, we do not assume yet the upward force from your AY. Okay, so this is from load alone. Okay, your reaction is different. Since your load is always positive and upward, so we therefore plus 63.706 here. Okay, upward. Since this is a load and then downward, so this is negative. So we have negative P. Okay, so this is part of your shear equation, and we have moment load which is negative P times x minus A. So here our A is is the distance of this load from your relative from your leftmost support. Okay, so here the distance from our leftmost support here is 2. So our A is 2. Okay, from the formula, since we have, since this is at support, so we directly multiply it by x. So 63.706 x minus load 75 times x minus A. Your A here is 2. Okay, so can you see it? Negative px times A. So we do it here. So your P is 75 here, your point load, and then your A is 2. So that's why we get this value. So this is your formula. Okay, you can simplify this or you may not simplify this. The important thing is you can construct properly your shear and moment diagram. Okay, and then the last is from x is equal to 4 to x is equal to 8.5. So if this is the case, okay, this is already our drawing. Okay, we have 75 here. Then we have AY is equal to 63.706. Then we start our diagram, which is a triangular load. Okay, so this is any value x. So our V here is equivalent to 63.706. Okay, the reaction here. Okay, we do not include the AX equals 0 because it's already 0 and it's horizontal. So only the vertical. So 63.706 minus 75 minus, okay, what shall we do when triangular? Okay, so we have a 16 kilonewton load. Okay. 16 kilonewton meter. We go from this diagram. Okay. So use this diagram, class. Okay. Here. This is from our part 1. Okay. So here we have triangular load. Your shear equation is negative W times x minus a squared over 2r, where a is the distance from your leftmost support to the start of your distributed load W. So it should be increasing order. If it's in decreasing order, it's another thing. Okay? Times L. Your L is the length of your distributed load. Okay? So here, because it's triangular, we use this formula. Negative W times x minus a squared over 2L. And for moment, negative W times x minus a squared over 6L. So we have, okay, we have 16 times x. Your a here is, this is 2 meters, this is 2 meters, so we start at 4. So x minus 4, okay, so since the beginning of your triangular load is 4 meter, okay, squared over 2, the length is 4.5, so 2 times 4.5, okay, or 9, okay, we can say 9 directly. 2 times 4.5 is 9, okay, so this will be our shear equation. Okay, no, we simplify it first. Okay, we add all the constants. So 2 times 4.5. So, okay, we take it as it is, 2 times 4.5. So, your V is negative 11.294 minus 16 over 9 x minus 4 squared. So, this is your V. What about your M? Your M is from this, okay? If it's triangular, here, negative W times x minus a, okay? So we have here, it should be 3, and this is 4, okay? So may I correct myself, this is 4, okay? 3 and 4, okay? Squared, since the integral of your shear equation is your moment equation, so it should be integrated, okay? So you integrate this one, you get this one. You integrate this one, you get this one, and so on. Okay? So 6L to the power of 3, okay? So this is to the power, I know, square, this is right. So we have, okay, so we have 63 point, we start at point load, so we have 63.706 x, since it is the leftmost support, minus, okay, 75 minus 75 acting 2 meters from the support, so x times x minus 2, then we have negative 16, okay, times x minus 4 from to the power of 3 times 6 times 4.5, okay, 6L, since L is 4.5, so 6 times 4.5, 6 times 4.5 is 27, okay, 27, so this is 27, so therefore this is your formula for M. So now on, okay, we check, okay, third, okay, to the power of 2, 3, 4, okay, so it's correct. So this is the shear and moment equations for each section, okay? So since we have section 1, this is 63.706, so from whole length of the section 1, it is 63.706. Okay, it's constant. And then from 2, okay, so since this is 75 kilonewton, this will be a sharp downward. It became suddenly negative 11.294 at x equals 2 to 4. So there is another shear here. Okay, negative 11.294 kilonewton. Okay, then okay, this is also negative 11.294. And then we have this formula. Okay? So obviously, when x is equal to 4, we get 0, negative 11.294. So what if at the end, 8.5? So let us check. Minus 16 divided 9. Okay? Okay, we transpose, we substitute directly. Minus 4 squared. We have negative 47.294. Since this is a 1 degree curve, so this will be a 2 degree curve here, or parabolic. So that is it, okay? So I'm sorry. It should be lower than this, so it will be like this. So this is negative 47.294. And then this is not the end. Since we have an upward force of 47.294, so it will eventually settle at 0. Okay, so this is your shear diagram. What about our moment diagram? Okay, so then again we substitute. Okay, so when m is equal to 0, so when x is equal to 0, your m is equal to 0 because you just multiply it. Okay, so it will be 0. And then when x is equal to 2, which is the end of section 1, we have 63.706 times 2 equals 127.412. It will act like that, okay? Okay, so please do remember, since this is a 0 degree curve, although it is flat, it is called 0 degree. So, okay, this is 0 degree curve. Oh. So this will be a 1 degree curve, and 1 degree curve is continuously upward. Okay, it is found on our part 1. Okay. Then we have the second for section 2. Okay, we all know that at x equals 2, 2 minus 2, this will become 0, the same as this. But we go directly at the end. So when n equals 4, so 63.706 times 4 minus 75 times 4 minus 2. So we have 104.824. So we have, since this is a straight line and 0, so this is a 1 degree curve, or just, okay, downward, linearly downward. This is 104.824. Okay, this is kilonewton meter. I'm sorry. 24 kilonewton meter. And then lastly, we check if we get the same, if we get 0 when x equals to 8.5. Okay, so we all know it's just, okay, it has the same value when x is equal to 4. So what if it became, so what if x equals to 8.5? So we substitute. Minus 75 times 8.5. 8.5 minus 4 to the power of 3. So we have 0. 1 times 10 to the negative 3 is practically 0. Okay? So because we have round off our values, so don't expect that at the end, you will get exactly 0. It should be very small number like 0.001, negative 0.002, or like that. Okay? So since this is a 2-degree curve, 1 degree load, 2-degree curve here, this will be a 3-degree downward curve. So it will be not linear. So it will be like this. Okay? So just assume that this is a curve. So this is a 3-degree curve. And then it will end at 0. And start at 0 and end at 0. So that is, okay? So this is a 3-degree curve. So that is our third example. Okay? So please take note of the first video that I posted. Okay? So this is our solution. Okay? So this is part 5 of our series. And then we will have another example, I guess, part 6. Okay? Shear and moment equations. This is part 5, and then we will have another example in part 6.